Hi everyone. Welcome back. We are still sort of in chapter 7.1, really trying to make sure that we fully understand the first law of thermodynamics and what it means before we really start going into things like reactions and trying to figure out the energies of systems whenever we have things changing. So I promised you guys that I would talk about the first law of thermodynamics at the very end of our last video. In the last video, we really talked about the difference between heat and work and how these things are inexact differentials and how in order to work with these, we have to take small steps along the process, and we called that a reversible process. Well, so now I'm going to put it all together in what is known as the first law of thermodynamics. The first law of thermodynamics really says that energy is constant. But in more specific terms, it says that the system and the surroundings exchange energy with each other through work and heat. And so if we put that into an equation, we get that dE is equal to dQ plus dW. Now remember, these dQ and dWs, these are inexact differentials. So we have to take into account the path that in the history or the way that heat and work occur. And so when we talked about our little elephant guys in their containers, we said that if the surroundings transfer heat to the system, that Q is greater than 0. And if the system does work on the surroundings, then work is less than 0. And we're going to make sure that this sign directionality makes sense. And so that's kind of where we're going today. Okay, so let's make sure that we have some vocabulary around the direction of the total energy change or the energy flow. If something is endothermic, that means that heat leaves the surroundings and enters the system. And so Q is positive. And if we draw that as a picture, it means that our energy is going from the reactants at a low energy to the products at a high energy. And this is the energy of the system. And that energy of the system is coming from the surroundings. Because remember that energy is constant. It has to come from somewhere. Now, if we have the opposite situation when something is exothermic, that means that heat leaves the system and enters the surroundings, or Q in that case is negative. And so what we have in this case are that the reactants are at a higher energy than the products, and during the process of, say, a reaction, the energy decreases. And remember that this is of the system. And so if the energy of the system decreases, that means that energy has to go into the surroundings. And really, if we put this into what do we observe, endothermic means that it feels cold. So this is something like ice melting in a glass of water. That it feels cold because it's pulling energy from the surroundings in order to melt that ice. Whereas exothermic feels hot. And so exothermic is like a fire burning, that the energy is going from the system to the surroundings, and we feel that as that heat. But remember that heat is not the only thing, that is not the only form of energy that is transferring. Work is also occurring. So there's really two different types of work. One type is expansion, and this is when the system goes from a small volume to a large volume. So V1 is less than V2. Or we can say that delta V is greater than 0. Our final volume is bigger than our initial volume. When this happens, this is expansion. And for expansion, work is defined to be less than 0. Work is negative because remember that work is equal to minus PdV if it's work reversible. And so if our dV is positive, in this case, in expansion, then our work has to be negative. And in this case, we say that work is done by the system. And so to think of this, to remember this, I always think about when I lived in Boston and trying to get onto the bus or the subway. And in order to get into that space, I had to do work on my surroundings. I had to move people to expand out some free space for me to be able to get on. And so it takes work to get done by the system, me, to be able to get onto that crowded bus. Now the reverse is compression. And so this is going from when V1 is greater than V2. And this is when work is being done on the system. And so this is if I'm already on the bus, the crowded bus, and someone else gets on, I get pushed, I get compressed by my surroundings into a more uncomfortable position, even closer to people. And so in this case, the volume change is less than 0. I'm getting into a smaller area. And that means that with work being reversible, being equal to negative PdV, if dV is negative, that means that work is going to be positive. Okay, so now that we kind of have a sense of this heat flow, the first law of thermodynamics is saying that change of energy is equal to the change in the heat plus the change of the work. And internal energy is a state function. And this means that if I think about my energy and I start at E1 and I go to E2, it doesn't matter if there are several steps along this route. All that matters is my final and my initial positioning. It doesn't matter how many steps along this route that happen to take. The delta E is equal to E final minus E initial. And that is how we know that is how we define a state function, that it is path independent. We don't have to think about this reversibility. Instead, we can just think about the beginning and the end. And that means that we can do regular normal integrals and be able to figure out what this delta value is. Another thing with internal energy is that internal energy is a function of volume, temperature, and moles. And so this means that energy really only depends upon a few macroscopic parameters. And so macroscopic parameters are things that are the big things. They're the big things that we can measure, like volume, temperature, amount. Internal energy does not depend upon the history of the system or the positions and the momenta of all of the particles in the system. So we can figure out this energy or this change of energy during a process without knowing everything about the atomic and electronic parts of our system. And this is kind of nice. This is kind of bigger than what we've been thinking about in statistical mechanics. But it makes this kind of nice because we are now reliant upon things that are fairly easy to measure. We're not dependent upon the entropy and the quantum states of each individual molecule. Okay, so in the next video, we're going to try to make the link between this kind of macroscopic view of internal energy and the statistical mechanics more microscopic view of internal energy, and try to make sure that our microscopic and our macroscopic really do align with each other. Because that's a big key piece of making sure that our models are accurate.